Hello and welcome back. Another lecture from organic chemistry. In this lecture, we're going to go through ozonolysis as a method that we can use it to generate aldehyde or ketone functional groups. In ozonolysis, we will be dealing with the cleavage of double bond, and this double bond depends whether it's carrying hydrogen on one side of it or not. It can create aldehyde or ketones. In the absence of hydrogen, the product always will be ketone. Now, we need to slow the reaction, and otherwise we might go through like over-oxidation, and we can turn actually aldehyde to carboxylic acid. So we need to have a reagent, reducing agent, and the reducing agent we can use dimethyl sulfide or zinc in the presence of water to slow technically the process. And so as you see, wherever we have a double bond, this double bond is going to go through cleavage, and then we will replace the double bond technically by oxygen atoms. Now, if we have a hydrogen atom attached to the double bond, then we will get aldehyde. Otherwise, we will get a ketone. So on the left side, because I have two substituents attached to carbon, and that's going to give me ketone. And as you see here, we got a ketone. But on the right side, we have hydrogen and a methyl substituent attached to the double bond, and that's going to give us an aldehyde functional groups. The process, as you see, is going to start with the insertion of the ozone molecule. It has two resonance structures, and I showed the resonance structures on the right side of this slide. And so as you see, the terminal, like one of the terminal oxygen, it can have a negative charge, while the central one, it will be positive. And the negative charge, it can move from the right to the left side of the molecule. So the first step, this negative charge, it will be inserted to the double bond, and it's going to generate a negative charge on this carbon, and then a negative charge, it will go after oxygen with a double bond. And now we got such a cyclic molecule. This cyclic molecule, very soon, it will go through a cleavage, and it will give us a carbonyl group. And other side is kind of like a carbonyl, but is carrying a peroxide the group. Now, this oxygen, it can actually attack the carbonyl, because carbonyl, it has sp2 hybridization. So I'm going to say this one, it has sp2 hybridization, and that carbon, it can attack. So that oxygen, it can attack it because it's going to behave as a nucleophile. And if that one happen, very soon, like we will generate a negative charge, or we will get a negative charge on this oxygen. And now we have, in one side we have ether, and other side we have peroxide. So this is ether, and other side we have peroxide. Peroxide is not stable, and it can go through technically like a cleavage very soon. And sulfide is going to facilitate that process. Sulfide, it has two lone pair, and it will go after one of this oxygen. And if we go after that oxygen, and then the oxygen, it will give up the lone pair to this oxygen. And so I'm going to say technically that double bond, it will be shared with carbon, and carbon, it will give up the electrons to oxygen, and oxygen, it can give them to carbon. And technically I will get this. Okay, I will get double bond there. And so as you see, I got two carbonyl functional groups there. Now let's practice some example. I wrote a bunch of molecules, and some of them, they have like a hydrogen attached to the double bond, some not. And I want to see what's going to be the what are going to be the product in each case. Okay, so one the first molecule, I have a double bond. I'm going to highlight the double bond. So that's my double bond. Let's highlight it. Next, I'm going to highlight any substituent I have there, and I do have one hydrogen there. Okay, next step, I'm going to break the molecule from wherever I have the double bond. So we will have a cleavage of the double bond. And this one is a secondary carbon. That one is that carbon is going to be, forgive me, this one, it will be a tertiary carbon because it's attached to 3 carbons. And this one, it will be a secondary carbon. And so what's going to happen, that carbon, like the tertiary one, okay, it will lose a connection with the neighbor, with the secondary carbon, and it will turn to ketone. Still, I have two substituents attached to it, and those are two substituents. And other side, I have this group. That group, if you cut the double bond, you will have hydrogen and methyl. I'm going to show hydrogen and methyl attached to this carbon. So here you go, hydrogen, and we're going to have a methyl and also a double bond, and that's going to be aldehyde. So because I had one hydrogen attached to the double bond, and I'm going to get aldehyde, and I got it. And other side, because there is no hydrogen attached to the double bond, it will give me only ketone. Again, let's highlight the double bond. Here you go, the double bond. And now I'm going to break this double bond. When I break this double bond, I will get ketone there. Why ketone? Because we have two substituents. We have the cyclopentyl and methyl attached to the carbon. And so that's going to be ketone. And other side, I have a carbon attached to 2 hydrogen. Let's show the 2 hydrogen. And now we're going to replace the double bond by double bond with oxygen, and that's going to be formaldehyde. And so this one is going to be aldehyde. Okay. Now, I said this one, if you don't slow the process, you might get over-oxidation. What does it mean? It means like maybe this formaldehyde, because it has oxygen and hydrogen attached to it, it can go through over-oxidation, it will turn to carboxylic acid. So technically the product is not going to be, the final product is not going to be aldehyde, it will turn to carboxylic acid. How about the ketone? No, ketone stay as it is, and we're fine when it comes to ketone. And I showed in like, on purpose, I put some example that I changed the condition and I added hydrogen peroxide plus the ozone. So let's go back. And then here, I had reducing agent or reductant, because I wanted to slow the process. But next step, like next example, I added H2O2, which is oxidant. This one is oxidant, is not actual reducing agent. And so that's gonna, actually push the reaction to one step more, and it will turn aldehyde to carboxylic acid. Okay, so again, let's highlight the double bonds. Here you go. Those are the double bonds. And whenever we have double bond, we're going to break it. And so I'm going to break the double bond. And that's going to give me, okay, it's going to give me like technically two carbons that they are carrying, hydrogen atoms. So I'm going to say, because I have hydrogen atom attached to each carbon, the process, it will go over oxidation, and it will give me carboxylic acid. Okay, so not aldehyde, be careful, because there is a hydrogen there, the process went through another step of oxidation. And how about the right side? Right side, again, we will get, okay, so that one also gave me acid. And in both cases, because I had hydrogen attached to the double bond, I got 2 carboxylic acid. Okay, another example, okay, one side of the molecule does not carry, any hydrogen. So that's going to give me a ketone molecule. And it's going to stop there, but other side, because it has hydrogen attached to it, it will go over oxidation and it will give us a carboxylic acid. Okay, another one, let's break the molecule from here. And next thing that I'm going to do, and I'm going to label this molecule, and I'm going to start it from here. 1, 2, 3, 4, 5, 6. Okay, and so I have 6 carbons there, and between 1 and 2, I had I have double bond, and 1 also I have a substituent, which is methyl. Okay, so let's say we this one is our substituent, and we're going to put carbon number 1 here. That's going to be carbon number 1, and because it doesn't have any hydrogen attached to it, and so that's going to give us a double bond with oxygen, and it will turn to carbonyl. But other side, it has hydrogen atom attached to it, and because it has hydrogen atom, it will go through over oxidation and it will turn to carboxylic acid. And okay, so if I count number of the atoms that I'm dealing with, 1, 2, 3, 4, 5, 6 atoms. And like the first methyl, I treat it as a substituent attached to the carbonyl. Okay. Okay. Another one. Let's again go after the double bond. We're going to break the double bond from there. And so that's going to give us a carbonyl attached to 2 substituent, and both of them are not hydrogen. So we're going to get ketone. And second molecule is a carbon that is carrying 2 hydrogen. You expect this one to turn to formaldehyde. But because we can go through over-oxidation, and in this case, because we have 2 hydrogen, we can go 2 steps more. So the first step is going to be this. The formaldehyde, let me move this one. This molecule, it will turn to acid. In another step, this one is going to go through another oxidation, and it will turn to CO2. So the final product is going to be technically a ketone plus CO2. We're not going to see the formaldehyde or the carboxylic acid. So I'm going to erase those 2. I'm going to erase these 2, and I'm going to say the final product, just simply, it will be this. Carbonyl, the ketone plus CO2. Okay. And again, the reason for it was because we had another oxidizing agent beside the ozone. So the reaction, it can go through another step of oxidation. Let's practice more example. I have a diene molecule, and this one is going to go through oxidation, ozonolysis, and the presence of reducing agent. So I'm going to do this. I'm going to here say 1, 2, 3. Why did I, did not go through the double bond? Because I want to show how many, carbon are between the double bonds I have. Other side, I have 1, 2, 3. Okay, so the molecule, we're going to chop it from there. And this one also just cut the molecule from 2 places, and you will get this. And let's say this one is carbon number 1, that's 2, and this one 3. And what do I get? Carbon number 1, it will go through oxidation, and because it has hydrogen attached to it, it's going to give us an aldehyde. And carbon number 3, also it will give us an aldehyde functional group. So, and because they are symmetrical, these two are identical. So I'm going to say I will get 2 mole from this molecule. Okay, so we get 2 moles from the dialdehyde molecule, okay, or diol molecule. Okay, so the correct answer for it is going to be number 5, and that's a molecule actually that we should choose as final product. Okay, another one. Okay, so we have a molecule, and its component A went through an ozonolysis and it gave us 2 product, and now we want to know what was the starting component. Okay, let's highlight these 2. Okay, this one is ketone, and that one is aldehyde. Okay, that means one side of the double bond, I should have hydrogen attached to it. Okay, how do I tackle this this type of question? Just simply redraw the molecule and put them in a way that the double bonds are facing to each other. Okay, when I say double bond, I'm talking about the carbonyl groups. Okay, so this is the first molecule. You have a carbonyl, draw the carbonyl this way, and what else? We have a methyl attached to it. Other side, we have a carbonyl, and we have hydrogen attached to it, and also an ethyl group. Okay, now highlight those double bond. Okay. Highlight those and get rid of oxygen atoms and just simply pair them. Okay, and if I pair them, I will get this. I will have a phenyl ring attached to a carbon, this carbon attached to methyl. What else? We'll have a double bond with carbon. That carbon, it has hydrogen and ethyl group. Okay, so now I should look for, let's see, molecule that one side of the double bond, it has methyl and phenyl group. And methyl and phenyl group. And other side of the molecule, we're supposed to have hydrogen and ethyl group. Here you go. Other side of the molecule, we have hydrogen and ethyl group. So the correct answer in this case is going to be A, and A is going to be the correct answer for it. Now, you might say, what are the product for 2, 3, and 4? Let's write them. Okay, and I'm going to start with 3 and 4 because I don't have a space for 9 and 2. So if I cut the molecule from there, that's going to give me such a molecule. So I get ketone because I don't have any hydrogen attached to the double bond. That's going to give me only ketone. Yes, they are not identical because it's not symmetrical, double bond. And other side, okay, other molecule, this one or number 2, both they have hydrogen and the double bond, so they will give us an aldehyde. Okay, this one is going to give us such a molecule. And how about this piece? That piece is going to be a carbon, CH3, attached to a carbonyl, and that carbonyl attached to hydrogen. So this one will be aldehyde. Well, that one was ketone. Okay, but how about number 2? Number 2, let me make space for it. This is the molecule that we're talking about. Let me double check it. So there is a hydrogen atom here, double bond, and then we have methyl. Okay, again, let's highlight the double bond because there is hydrogen attached to the double bond. We're going to get an aldehyde. So that's going to give us such a molecule. This is aldehyde. And then the top molecule, it will turn to, let me write it here, the top one, it will turn to something like this, which is ketone. And that's going to be a product of the second part of the double bond. Okay, and this is going to be the end of this lecture, and thank you very much.